Dear learners, it is my immense pleasure to welcome you all once again to this module. The title of the module is Eigenvalue and Eigenvector. In this module, we are going to learn about characteristic matrix, characteristic polynomial, characteristic equation, eigenvalue and eigenvectors of square matrices and its properties with suitable examples to demonstrate these concepts. An eigenvector or characteristic vector of a linear transformation is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. The corresponding eigenvalue, often denoted by lambda, is the factor by which the eigenvector is scaled. The geometrical idea of an eigenvector corresponding to a real non-zero eigenvalue is that of a vector which points in a direction in which it is stretched by the transformation, and the eigenvalue is the factor by which it is stretched. If the eigenvalue is negative, the direction is reversed. In linear algebra, we frequently come across the need to evaluate square matrices raised to finite powers. Computing the characteristic equations using the corresponding eigenvalues helps us to evaluate these easily. We shall see a definition now. Suppose A is a matrix, that is we denote that by a Aij, that is an n by n matrix, and lambda be an arbitrary number. Then the matrix lambda in minus A, where in is the identity matrix of order n by n, is called characteristic matrix of A. That is, if A is equal to A11, A12 etc. A1n, similarly it goes till An1, An2 etc. Ann is n by n matrix, then the characteristic matrix of lambda I minus A is lambda minus A11, A12 etc. A1n, A21 lambda minus A22 etc. A2n, and the final entry is An1, An2 etc. lambda minus Ann. You can see the diagonal entries alone vary. Let A be an n by n matrix. The determinant of the characteristic matrix lambda in minus A is called characteristic polynomial of A. Clearly, characteristic polynomial of A is a non-zero polynomial of degree n in the indeterminate of the form b0 plus b1 lambda plus b1 lambda square plus etc. plus bn minus 1 lambda power n minus 1 plus bn lambda power n, where bi are scalars. The equation mod lambda in minus A is equal to 0 is called the characteristic equation of the matrix A. So, we are going to determine the characteristic equation of the matrix A is equal to 1 0 0 1. First, obtain the matrix lambda in minus A. The usual procedure, lambda in is identity matrix and A is the matrix given by 1 0 1 1 0 1, and if you do that, you have lambda 0 0 lambda minus 1 1 0 1. At last, that gives you lambda minus 1 0 lambda minus 1 as a 2 by 2 matrix. That is, lambda in is equal to, that is lambda in minus A is equal to lambda minus 1 0 lambda minus 1. And we are going to determine the characteristic polynomial as follows. It is earlierly I have mentioned that as a mod, but that is a determinant, not mod. So, here we have because we are talking about the matrices here, this is determinant. So, determinant lambda in minus A. So, this is if you find this determinant, you have lambda minus 1 multiplied by lambda minus 1, that is called as lambda minus 1 the whole square, minus of 0, that is lambda square minus 2 lambda plus 1. Thus, the characteristic equation of the matrix A 1 1 0 1 is given by lambda square minus 2 lambda plus 1 is equal to 0. We shall see a definition now. A real or complex number lambda is called an eigenvalue or characteristic root of an n by n matrix A if there exists a non-zero n by 1 matrix X such that Ax is equal to lambda x. Any non-zero vector x satisfying the condition Ax is equal to lambda x is called eigenvector corresponding to the eigenvalue lambda. So, we shall see some remarks. Let A be an n by n matrix of real or complex numbers. Then lambda is an eigenvalue of A if and only if determinant of lambda in minus A is equal to 0. Second one, if lambda is an eigenvalue of A, then any non-trivial solution of lambda in minus A multiplied by x is equal to 0 is an associated eigenvector. We shall see some additional properties of eigenvalues. Let A be an arbitrary matrix of complex numbers with eigenvalues. The trace of A is defined as the sum of its diagonal elements and also the sum of all eigenvalues. The determinant of A is the product of all its eigenvalues. The matrix A is invertible if and only if every eigenvalue is non-zero. Now, we shall see some examples. Look at the first example. We are having a 2 by 2 matrix A. The first row is 1, 2 and the second row is 0, 2. For this matrix, we are going to find its eigenvalues, and corresponding to the eigenvalues, we are going to find eigenvectors. Okay. So, how do we find eigenvalues? What you have to do is, first you have to find the matrix A minus lambda I, and after that please take determinant, and from that we will be getting a characteristic equation, and if you solve a characteristic equation, then the roots of the characteristic equation will be the eigenvalues of the given matrix. So, that is the procedure. So, now, this is Ax minus lambda x. So, A minus lambda I x is equal to 0. So, here this I is an identity matrix of order 2. So, now if you consider the determinant of A minus lambda I and equate to 0, so does it matter whether you find A minus lambda I or lambda I minus A, there is no effect on the eigenvalues that you are going to find. Therefore, I am going to take lambda I minus A. So, this is equal to lambda, now I is 1001 minus 1202. You can also have A minus lambda I also, and therefore, this is lambda 0 0 lambda minus 1202. So, this is lambda minus 1, 0 minus 2 is minus 2, 0 minus 0 is 0, lambda minus 2 is lambda minus 2. So, what you have to do? You have to find the determinant and equate the value to be equal to 0. So, if you find the determinant, you have lambda minus 1 multiplied by lambda minus 2, and then minus of 0 multiplied by minus 2, that is again 0. Therefore, what you have is lambda minus 1 multiplied by lambda minus 2 is equal to 0. That is, you have lambda square minus 3 lambda plus 2 is equal to 0. That is, lambda minus 1 lambda minus 2 is equal to 0. So, this is your characteristic equation, and from here you can easily see that the value of lambda is equal to 1 and lambda is equal to 2 will be the roots of the equation. Therefore, the eigenvalues for the given matrix are 1 and 2. Now, we finished our first task, that is to find the eigenvalues. The eigenvalues we have computed, and after that what we are going to do? We are going to find eigenvectors corresponding to these eigenvalues. First, we will take lambda is equal to 1 and we will find the eigenvector corresponding to this eigenvalue 1, and then we will take lambda is equal to 2 and then we will find the eigenvectors corresponding to lambda is equal to 2. Okay, now we shall move to compute eigenvectors. So, now here lambda I minus A, right? Here lambda is equal to 1. Therefore, 1 I minus A x is equal to 0. That is what I am going to consider. So, 1 I is nothing but I of order 2, that is 1 0 0 1 minus A is the given matrix 1 2 0 2 and x is x1 x2. You have 2 vectors is equal to 0 0, 2 components of the vector. Therefore, this is 1 minus 1 is 0, 0 minus 2 is minus 2, 0 minus 0 is 0, 1 minus 2 is minus 1, x1 x2 is equal to 0 0. And if you find the product of these two matrices, this is 1 by 2 by 2 matrix, this is 2 by 1 matrix, you can find the product, and if you find the product of these two, you have minus 2 x1 and minus minus 2 x2 minus x2 is equal to 0 0. So, from here you can tell the value of x2 is equal to 0. And what is the value of x1? x1 is arbitrary, you can take any values of x1. So, that is what we mean from here. Therefore, since x1 is arbitrary, take any value, let it be a. Therefore, the eigenvector corresponding to the eigenvalue lambda is equal to 1 is, this is an arbitrary value a, and therefore x2 you have 0, a and 0 is the corresponding eigenvector 2 by 1 matrix. And then corresponding to lambda is equal to 2, we have to find eigenvectors. We have to follow the similar procedure. So, instead of lambda I, here we have substituted 1, right. So, now we are going to substitute 2, 2I minus a, x is equal to 0. So, I value is 1 0 0 0 1. If you multiply 2 with I, you have 2 0 0 2. So, that is what we have here. Minus a is 1 2 0 2 and x1 x is x1 x2, this is 0 0. Now, this is 0 vector, so therefore 0 0. So, now if you find this, you have 1 minus 2 0 0 x1 x2 is equal to 0 0. So, from here you have x1 minus 2 x2 is equal to 0, and which means that x1 is equal to 2 x2. So, if you take x1 to be equal to a, then x2 is equal to a by 2. Therefore, you have to give one arbitrary value to one of the variables. I am giving arbitrary value to x1, and that leads me x2 to be equal to a by 2. So, if you substitute the any arbitrary value for x2, then for example, if you substitute x2 is equal to a, then your x1 is equal to 2a, that is it. So, that is also your choice. Therefore, the eigenvector corresponding to lambda is equal to 2 is a by 2, where a is an arbitrary number, real number. So, now this is how we compute eigenvalue and eigenvector. We shall see some more examples for our clear understanding. So, let us move towards another example. So, here I am having a matrix called 1 1 1 1, and again it is a 2 by 2 matrix. I am going to find the eigenvalues. For that, first step is I am going to find lambda I minus a and the determinant of it. So, this is lambda 0 0 lambda minus 1 1 1 1, that gives me lambda minus 1 minus 1 minus 1 lambda minus 1. If you find the determinant and equate to 0, you have lambda minus 1 multiplied by lambda minus 1 minus of minus 1 multiplied by minus 1, that is minus 1 is equal to 0. So, lambda minus 1 multiplied by lambda minus 1 is lambda minus 1 the whole square. That will give you lambda square minus 2 lambda plus 1, and already you have minus 1 here. Therefore, plus 1 minus 1 becomes 0. Therefore, you have lambda square minus 2 lambda is equal to 0. From here, if you take lambda outside, you have lambda multiplied by lambda minus 1 is equal to 0. That is, lambda is equal to 0 is one root and lambda is equal to 1 is another root. Therefore, here the eigenvalues of lambda is equal to eigenvalues of this matrix are 0 and 1. So, here this is lambda square minus 2 lambda, this is lambda multiplied by lambda minus 2, not 1. Therefore, this is lambda is equal to 0 and lambda is equal to 2 or 2 roots of the equation, characteristic equation. Therefore, these two are eigenvalues of the corresponding matrix 1 1 1 1. So, now we have computed the eigenvalues. Our next step is compute eigenvector corresponding to these two eigenvalues. So, first for lambda is equal to 0, if you substitute here, what will you have? You have minus 1 minus 1 minus 1 minus 1 x1 x2 is equal to 0 0. That gives you minus 1 minus x1 minus x2 is equal to 0, and again you have the same element here. Therefore, that from here we can say minus x1 is equal to x2. Give an arbitrary value to one of the variables, you will get the answer for the next variable. Therefore, here the eigenvector is a and minus a corresponding to lambda is equal to 0, where a is arbitrary. And next we have to compute eigenvectors corresponding to lambda is equal to 2. So, here instead of lambda I have substituted 2, I have computed 2I minus a x is equal to 0. So, from here I am obtaining this matrix, that is this equation 1 minus 1 minus 1 1 x1 x2 is equal to 0 0, and what you have to do is you have to again find the eigenvectors corresponding to this eigenvalue 2, no. Therefore, equate the equations or equate the corresponding elements. You have x1 minus x2 is equal to 0 and minus x1 plus x2 is equal to 0. That will give you x1 is equal to x2. In the earlier part we had x1 is equal to minus x2, but here we have x1 is equal to x2. and give an arbitrary value to one of the variables. So, that is x1 is equal to a. If you assume the value of x1 to be a, an arbitrary value, then your value of x2 is also a. Therefore, a is the eigenvector corresponding to lambda is equal to 2. So, now we have computed eigenvalues and eigenvector for the given matrix. Now, we shall see one more example. So, this is a 3 by 3 matrix 1 2 3 0 2 3 0 0 3, and you have to note that you can find the eigenvalues and eigenvector corresponding to only the square matrix as we talk about the determinants. Therefore, here I have taken 3 by 3 square matrix, that is I am computing lambda I minus I, that is giving me the determinant to be lambda minus 1 minus 2 minus 3, 0 lambda minus 2 minus 3, 0 0 lambda minus 3 is equal to 0. From here, if you find the characteristic polynomial is lambda minus 1 lambda minus 2 multiplied by lambda minus 3. The characteristic equation is lambda minus 1 multiplied by lambda minus 2 multiplied by lambda minus 3 is equal to 0. So, from here you can easily see that values of lambda are 1, 2, 3 or forms the roots of the corresponding characteristic equation. Therefore, 1, 2, 3 are eigenvalues of the given matrix. So, we have successfully computed the eigenvalues. Now, corresponding to these eigenvalues, we have to find eigenvectors. The similar method can be followed as usual, whatever we have done for the previous two problems. Similar method you can follow, and here at last we are getting the eigenvectors corresponding to lambda is equal to 1 to be a 0 0 and corresponding to lambda is equal to 2 to be 2a 0, corresponding to lambda is equal to 3 to be a, 2a and 3a. So, this is how we usually compute eigenvalues and eigenvectors for a matrix. Next, we shall talk about some theorems, and we shall see how the theorems, what the theorem says. The first theorem states that the eigenvalues of a triangular matrix are the entries on its main diagonal. The next theorem states if V1, V2, etc. Vr are eigenvectors that correspond to distinct eigenvalues lambda 1, lambda 2, etc. lambda r of an n by n matrix A, then the set V1, V2, etc. Vr is linearly independent. The next theorem states let A be an n by n matrix, then A is invertible if and only if the number 0 is not an eigenvalue of A and the determinant of A is non-zero. So, from the example itself, you would have noticed if you have an upper triangular and lower triangular matrix, the eigenvalues are the diagonal entries. You can verify it later, you can see the examples and you can verify it. So, now we are at the conclusion of this session. In this module, we learnt about characteristic matrix, characteristic polynomial, characteristic equation, eigenvalue and eigenvectors of a square matrices and its properties with suitable examples. I hope this module is of great use. We will see you in the next module. Thank you.